In this second tutorial, we will look at our final objective and be able to use the properties of logarithms. So let's flip over to this page in our notes and we'll look at some of our logarithmic properties. Our logarithms are representing our exponents. So these properties are really coming from our laws of exponents that we've already studied. When we're first looking at the product property, this is a property that says what to do with a logarithm that has a product as the number, m times n. Well, I like to go back into thinking about exponents and the laws of exponents. If I were multiplying two of the same bases together, we all know that we should be adding our exponents. So that's why this property is very similar. If I have a product inside a logarithm, I can separate the logarithm into two separate ones, so the log of m individually, and add that to the log of n. I can separate my product into two separate logarithms with a plus sign in between. And I know that because this is what I would do with the exponents here. I would add the 2 and the 3 in this case. This is an equal sign, so it does work both ways. If we have a logarithm of a product, we can split it into two separate logarithms, or with an addition sign. If we have two logs added up, as long as they're the same base, we can condense them back together into a single one by taking the numbers and multiplying them. So it does work both ways, like an equal sign represents a biconditional statement. It works both ways. The quotient property, I like to think of, a law of exponent problem like this. When we're dividing the same bases, what do we do with their exponents? We subtract them. So if we have the logarithm of a quotient, we can separate those into two separate logarithms. And the order, of course, matters. So we start with the one that's in the numerator, so the log of the m, and then take away the log base a of the n. So we can separate this quotient into two separate logarithms by subtracting the logarithms, because that's ultimately what we would have done with their exponents. We would have subtracted the exponents. And logarithms are just representing exponents, so this is basically an exponent, take away another exponent. So that's how I remember what to do with a quotient. Our third main property is our power property. And I like to think of something like this, where we have a power and we raise it to another exponent. What do we do with our exponents in this case? Of course, we multiply them. So if we have the logarithm of some number that's being raised to yet another power, we can take that power ultimately outside and make it like a coefficient out here. The p can be multiplied to the log base a of m. So it's like taking this exponent, this logarithm, and multiplying it by this exponent, which was the p, because that's what we would do with our exponents. In this case, we would multiply the exponents. So remember when we add them, remember when we subtract them, and remember when we multiply them, and try to remember that with your logarithmic properties. Before we get to the change of base property, I'd like to talk about two types of used logarithms. First, common logarithms. Common logarithms are logarithms that have a base of 10. We all have 10 fingers, and that's how we started to count on our fingers, and that's why we have exactly 10 digits in our numbers from 0 through 9. Every number that we know is created from one of our 10 digits, or a bunch of our 10 digits. So base 10 is our common logarithm. You very rarely will ever see this base 10 down here. If we had the log base 10 of something like x, we don't even write that 10. This logarithm is used so often that we just have this symbol, log of x. Meaning, if you do not see a base right here, it's assumed, it's implied that it's base 10. Now, I said that I was going to go back in our notes to one of our first examples. So if you would do that, remember this logarithm right here, we wrote log base 10 of 1000 equals to 3. Now we know that this is a common logarithm, and we actually will not write it with the base 10 anymore. We're going to write it simply as the log of 1000 is equal to 3. That is a common logarithm. Okay, oop, that's not it. There we go. So that's base 10. When you have a base of 10, we don't write the base, we just have this. The natural logarithms have a base of e. E is an irrational number, sort of like pi. I guess it's the second most famous irrational number, base e. So if we have log base e of x, we actually have a completely different symbol for this. We never use the base e except right here in our notes. We have a different symbol and we call it the ln, the natural log. And that's a different button on our calculator and a different symbol altogether. So when you see this ln of something, it's implied that the base that you don't see is like a little e right there. And we'll talk more about the number e later. So we've got common logarithms and we've got natural logarithms. Finally, our change of base formula. Our change of base formula says that we can take the log base anything of anything and rewrite it using common logarithms, or in fact using natural logarithms. We can take this logarithm and write it as the common log of the number divided by the common log of the base. So if you ever saw something like this, we can write it as the common log of the number divided by the common log of the base. Or we could use natural logs. The natural log of the number divided by the natural log of the base. That's what our change of base formula is. And that's really more helpful when we start solving our exponential equations. So these are our properties. If you want to make some flashcards to help you to memorize these, that's fine. Really, it just takes some practice using them. And that's what I'd like to do right now. Show you a couple of examples. Example number 4 has a bunch of different parts. What we're going to be doing is we're either going to be expanding or condensing. Expanding means separate into a bunch of pieces. Condensing means put it into a single piece. And we're going to be using the properties that we just had in our notes. So let's first look at the log base 3 of 9x. I see that I have a product here. And if I have a product, I can split this up into two separate logarithms using my product property and write it as the log base 3 of the first one plus the log base 3 of the second one, which is just x. Now, some people might think, oh, okay, that's it, we're finished. But I would call your attention to whenever you have numbers here. Sometimes we'll leave them, but sometimes they are numbers that we actually can simplify more. The log base 3 of 9 should be a number that we know. This is representing an exponent. It's the exponent that 3 has to be raised to become 9, and that is the squared. 3 is squared to become 9. So this logarithm can go away and get replaced with a 2. Not much to do with the log base 3 of x, so I'll write that. Our second example is the log of 21. Now I see that I'm missing a base, so that must imply that it's a 10, that this is a common logarithm. Okay, great. 21, okay, that's not very helpful. Maybe I write 21 as a product. Maybe I write it as 3 times 7, or 7 times 3. That's fine, because then I can employ my product property again and split this up into two separate logarithms, the log of 3 plus the log of 7. I did this with a number so that you could check this in your calculator if you don't believe my properties. You can plug this right into your calculator using the common log button, the log of 21, and press enter and get some irrational decimal number, and then type in the log of 3 and add it to the log of 7 and see that you get the same number, because that's true. Let's use our product property one more time here. In part C, we have the log base 7 of a product of three things, 3 times x times y. That's fine. We can use our product and split it into three separate logarithms. The log base 7 of the first number, which would be 3, plus the log base 7 of the second number or factor, which would be x, plus the log base 7 of the last one, which would be y. I call attention to this, but this isn't really going to do anything. 7 raised to, I don't know what 7 would have to be raised to get 3. I'd have to figure that out later. So I know that I'm finished. Nothing more to simplify there. Let's look at part D. Part D, I'm now dealing with a quotient. And the quotient says that I can still split it up into two logarithms, but this time I'm going to be subtracting the logarithms. The log base 2, that's the numerator, take away the log base 7, that's the denominator. And again, the common log, base 10, it doesn't really help with the 2. Base 10 doesn't really help with the 7, so I know that I'm finished. Right now I'm just practicing using my properties. The log base 6 of 6 to the 6 divided by x looks very similar to this one. Of course, I have a different base, but it's the same idea. I'm using my quotient property. I'm going to write the log base 6 of 6 and take away the log base 6 of x. That's what my quotient property says. I can split up the quotient into two separate logs with a minus sign. But this one, now I can simplify more. What does this base 6 need to be raised to become 6? Well, that should be obvious that it's just the first power. 6 raised to the first power becomes 6. So the log base 6 of 6 can be replaced by the 1. And not much going on here because I have because I have a variable. So that must be my simplified answer. Next, the log of x squared. Sure, I could see this as a product. I could write it as x times x, but I'm going to use my power property and say if I've got an exponent inside a logarithm, I'm just going to bring it right outside and write it as 2 times the log of just my base x. And that's it. Think about it, if you wrote this as x times x and you'd be using your product property, you'd split it up into the log of x plus another log of x. Well, then you'd have 2 logs of x, and there you go. Let's look at the next one. Looks like it's going to be the same thing. I've got an exponent inside a logarithm. Oh, this time it's a natural logarithm, but that's just a different symbol. That's fine. I'm going to bring that -3 right on outside, and I'm going to write that as as a coefficient, -3 times the natural log of x. And there you go. That's all we need to do. So these are all examples of expanding. This is what we do to expand. The last set of problems, we're going to be condensing, because now we have a couple different logarithms and we'd like to put them back together. As long as we have the same bases, we should be fine, and I see that I have the same base of 3. If I'm adding two logarithms, I know that I can condense them into a single logarithm by taking the two numbers, in this case 2 and 11, and multiplying them. I guess I don't need to put them in parentheses, but there you go. I condense two logarithms into one by using the reverse of the product property, and of course 2 times 11 is 22, so I could write that as the log base 3 of 22. That's condensing it, sort of putting it back together. Similar with this one, I've got a subtraction here, so I can condense these two logarithms into a single one. With the subtraction, I know that I'm going to be dividing the numbers. So I take the x minus 1, and I divide by the 5, and that's it. I'm just condensing that into a single logarithm. Please don't mess this one up. This is not the same thing as this. You don't take both natural logs and divide them. That's not what we're doing. We condense into a single natural logarithm and write it as a as a quotient here. Let's look at this next one. I've got two natural logs. I know that the bases are e, so that they're the same. So I can condense them together. This time I'm adding them up. So this time I'm going to multiply. Oops, that's supposed to be a 14. Multiply the 14 and the y. And actually, I guess that's it. I don't really need the parentheses, but not a problem there. Multiply the 14 and the y, and I've condensed it. This one, part K, I've got a number that's outside of a logarithm. Well, how did that happen? Somebody must have taken an exponent from inside and brought it outside. So to condense, I'm going to put it on back in. I'm going to bring the 3 back in here and put it on top of that other 3. So this should be 3 cubed. And we all know that 3 cubed is 27, so I'd like you to take that one extra step and just write it as a 27. So log base 2 of 27. 2 more to go. We've got the natural log of the cube root of x. I'm trying to figure out what we're supposed to do with this. Well, I remember that radicals are fraction exponents. So maybe it would make sense to write this not in radical form, but rather exponential form. If I have a cube root, that must be the 1/3 power, the 1/3 exponent. X to the 1/3 is the same thing as the cube root of x. Now I can see what we're going to do. This is actually an expansion one, where I'm going to pull this outside and write it as the 1/3 natural log of x. So that's a good example there. We had to convert it into the exponential out of the radical form. And our final one, log base 6 of 11. 11 is prime, so there's no way to write that as a product. So there's not much we can do here. This is one of my examples to show you the change of base form. Some people don't know how to evaluate this. In fact, I have no idea what 6 has to be raised to get 11. But I do know that the change of base formula says that I can rewrite this as the common log of 11 divided by the common log of 6. And then I could plug this into the calculator if I really wanted to. I just wanted to show you that that's how we would use the change of base formula when there's really nothing else we can do. We can just take those two numbers and put them into separate logarithms, common logarithms. We could do natural logarithms if we really wanted to. Thanks for watching this. I hope that this makes sense right now, and if not, then let's practice more in class, and I will see you then. See ya.